Welcome to the online training FPGA Business Fundamentals. My name is Justine and I will be your instructor for this course. During the presentation, you may pause, stop, and start this training at any time. On the left side of the window, you will find the Menu tab, which allows you to skip forward or backwards to specific slides. There, you will also find the Notes tab, where you can follow along by reading the script of this course. Today, we are here to give an overview of the FPGA market. This training was designed for people who are unfamiliar with or new to the business aspects of the FPGA industry. This will help give more context to the work we do here at Intel PSG, and at the end, you will be able to answer the questions why an FPGA and why an Intel FPGA. So let's get started. Now, two other hardware that the FPGA is frequently compared to are the ASIC, which is an application-specific integrated circuit, and an ASSP, which is an application-specific standard product. A great way to understand the differences between all three devices is by using this analogy. ASICs, ASSPs, and FPGAs are all like different types of signs. First, ASICs are like custom logos. They're custom made for one specific company or one specific brand. A lot of money and time is put into designing a logo. The colors, the fonts, everything has to be perfect. There's no taking back or tweaking a logo if a customer doesn't like it. So companies have to get it right the first time. But this risk and this investment is worth it for franchises that are large enough with national and international locations and a wide breadth of merchandise that they know this logo is going to be placed on. And just like an ASIC, once it's created, only one company can use it. ASSPs are like your standard help wanted and for sale signs. They are made for a very specific function, but common enough that you can get it at any hardware store. When you see a help wanted sign, it tells you one thing and one thing only. You know exactly what it does. But its purpose is still generic that it can be bought off the shelf. Unlike an ASIC, ASSPs are used by many companies across an industry, hence the name Application Specific Standard Product. These devices are normally standard across an industry. But if you ever needed to change the function, let's say from a help wanted sign to a for sale sign, you couldn't repurpose it. You'd have to get a different ASSP or a different sign. FPGAs are like whiteboards. They're extremely flexible and customizable. A whiteboard is a blank slate users can use to color, draw, or write anything. Intel provides you with the tools, erasers and markers of all different colors and sizes, but the quality of the design is heavily dependent on the expertise and the skill of the person creating it. Intel can provide IP like the magnetic letters and shapes to help aid in the design process, but you don't have to use it if you don't want to. Unlike the off the shelf sign, you can change the function of a whiteboard. You can write notes on it and then erase all of it and draw pictures. This reprogrammability is the defining characteristic of an FPGA. Now, the purpose of this training is to focus on the FPGA, but it is important to acknowledge that ASICs and ASSPs also have their advantages. From a high level, pros of using an ASIC/ASSP are its low per unit cost, low power consumption, high performance, and small unit size. Once manufactured, at high volume mass production, one die can cost cents, whereas an FPGA can cost tens of dollars. An ASIC can also reach clock speeds that are 2 times faster than that of an FPGA, all while consuming less power and taking up less area. However, ASICs and ASSPs are not without their drawbacks. First, ASICs have an extremely large non-recurring engineering cost, or NRE. This can run into the millions of dollars. This is the upfront cost needed before production and includes things like design cost, cost of simulation, mask costs, and software tools. The masks alone can cost millions of dollars. ASICs and ASSPs are also not flexible. Once they're manufactured and hardened in silicon, they cannot be upgraded. They also have a complex design flow and a long time to market. Developers aren't usually concerned with speed as much as they are with accuracy of their design. With such a high NRE, they have to get it right the first time. Time to market for an ASIC can be months, if not years. And if the silicon has any bugs or if any settings need to be tweaked, you'd have to start the process all over. But all of these cons can be addressed with an FPGA. And now we can begin answering the question, why an FPGA? From a very high level, I've categorized the benefits of an FPGA into four key pillars. Now, this is by no means a complete list of all FPGA advantages, but it does show the reasons you would choose an FPGA. First and foremost, FPGAs are reprogrammable and flexible. This is their defining characteristic. On an FPGA, you can reconfigure the hardware even after the product has been installed in the field, hence the name Field Programmable Gate Array. This feat is all encompassing. This is the umbrella that really enables all the other benefits listed. Next, FPGAs are future proof. They ensure product longevity. Because of their reprogrammability, they can be upgraded throughout the entire lifetime of a product. You don't have to physically remove and reinstall new hardware if you want to do something like add a new feature or fix a bug. Also, because of their reprogrammability, FPGAs bring a reduced time to market. They have little to no NRE and have a less complex design flow. This means that you can get your product out the door faster. FPGAs are great for prototyping and testing because you can quickly adapt to changing standards or alter product architecture. Lastly, FPGAs are market size optimized. This means that there is a very specific market size or volume range that FPGAs are naturally optimized for. If an application falls within this specific market size or specific volume range, FPGAs can be more cost effective than an ASIC. Now, later in the presentation, I'll go more into depth on this last pillar and the other three pillars, and we'll continue to discuss examples of industries and applications where these key benefits are really highlighted. Now, these are great advantages, but who are we serving? Who are our customers? Intel PSG has customers across many growing industries: data center, wireless communications, military and industrial, healthcare, finance, retail, and automotive, just to name a few. FPGAs have an extremely broad customer base, but target opportunities with mid to low volumes. More commonly, other types of hardware will focus on a few key customers, but who have really high volume opportunities. Now, this is not to say that FPGAs can never and will never reach high volumes, just in general, this is how the market has been. Now, looking at it from a support perspective, Intel PSG must create user guides, trainings, and other collateral that can be published on Intel.com and used more broadly across all users. Other business groups may be able to tailor trainings and support specifically to the needs of one customer, but that makes sense for them because the opportunity is high enough. In the FPGA market, support and support documentation has to service a wider range of customers across a wide range of industries. Now, expanding on those four pillars that were mentioned previously, FPGAs are future proof. They have a life cycle that is around double that of an ASIC. Most products, ASICs, GPUs, and CPUs, typically have a lifespan of 5 to 7 years, but FPGAs are built to last over a decade. Long FPGA life cycles really align well to the longevity of industrial and military products. I mean, just think about it. Machinery in a factory isn't upgraded every 3 to 5 years like a laptop, they're built to last decades. With an FPGA, you can send hardware updates, bug fixes, add new features, and even change the functionality completely, all through the entire 10 plus year lifespan of the product. This helps customers mitigate design risk, thereby reducing their total cost of ownership. But on top of being built to last, FPGAs are also perfect for short term intermediary use cases as well. The programmability of FPGAs makes them great for prototyping and developing. In emerging markets where standards have not yet been defined, FPGAs have a huge time to market value. Remember from the previous slide, ASIC developers aren't concerned with speed as much as they are with accuracy. They have to get it right the first time. ASICs have a long development and a long debugging cycle. This can mean reduced profitability over a product's lifetime. So, failing to have your product ready in a certain market window can cost a company a considerable amount of revenue. You risk a competitor's product being adopted and yours being considered useless. Historically, companies that are first to market have a huge advantage. They will capture and retain a majority of the market share. This is why companies will prototype and develop on an FPGA just to get their product out the door faster. An example of this happening today can be seen in the automotive and wireless industries. ADAS, which stands for Advanced Driver Assistance System, has many technologies and standards that have not yet been defined. LiDAR, safety regulations, camera standards, these are all constantly changing. Similarly, in 5G, technologies like millimeter waves, beamforming, and massive MIMO are still being developed and researched. But car manufacturers and telecom companies can't just wait for these standards to be defined. They have to be agile, they have to be able to quickly adjust with the market. But once these standards are solidified and crystallized, once companies have perfected their architectures, they will likely switch to a cheaper and more energy efficient ASIC. This trend of developing on an FPGA and then switching to a custom ASIC is a pattern we've seen with 3G and 4G and will likely continue with 5G. There will be a spike in FPGA usage as the technology is first introduced, and then it'll start to drop down as ASIC usage begins to rise. So, when exactly does this transition occur? At what point do companies decide to cross over from an FPGA to an ASIC? This graph shows when that decision is made. The point at which ASICs become more cost effective than an FPGA is commonly known as the crossover point. Now, this exact volume number will vary depending on application, process node, product, low end or high end, but in every case, volumes below the crossover point, FPGAs win. At volumes above the crossover point, ASICs win. The cost per unit is represented by the slope of each line, and since the unit cost of an FPGA is higher, the blue dashed line is steeper. As mentioned earlier, the NRE or non recurring engineering cost of an ASIC can be in the millions or tens of millions of dollars. So, relative to the NRE of an ASIC, initial cost of an FPGA is at or close to zero. This cost to volume ratio is what makes FPGAs market size optimized. This is what was alluded to earlier with the four pillars. In the blue highlighted region, the ASIC's high NRE becomes more cumbersome than the per unit cost of an FPGA. But as volume increases, the high per unit cost of an FPGA makes ASICs the more cost effective choice. And again, this exact volume can range from 1,000 units to 100,000 units, depending on the device, whether it's a Cyclone or a Stratix, process node 32 nanometer versus 10 nanometer, and of course the price sensitivity of the end application. Now, over the past 30 years, the total cost of an FPGA has gone down, with each advancement in process technology from 32 nanometer to 22, 14, 10, 7 nanometer. Cost of production has decreased substantially, and the slope has decreased. But as process technologies advanced, chip architecture has become more and more complex. And because of this increased design complexity, ASIC NRE has gone up. So, what this means? This means that with each process node, this crossover point has shifted to the right. This shift allows FPGAs to capture new opportunities with higher and higher volumes that we weren't able to capture before. As technologies have improved, we've been able to capture some of the ASIC market share. Take the broadcasting industry, for example, where FPGAs were traditionally used for prototyping. Now, control rooms have grown past just television studios. Now, new locations are starting to broadcast their own content. Sports venues, like professional and college stadiums, large churches that broadcast their sermons, concerts, music festivals, all of which have equipment running on an FPGA. And as this industry continues to grow, FPGAs continued to grow with it. But although there are a lot of new opportunities emerging, there will always be those applications that reach this crossover point, and companies will eventually convert to an ASIC. Going back to our 5G example, although FPGAs have become cheaper, At mass production, ASICs are still more cost effective, and our wireless customers will eventually reach a point where they switch to a better performing, more energy efficient ASIC. But with that said, to combat this crossover point and to capture as much ASIC market share as possible, Intel has acquired eASIC. Now, I won't get too into eASIC in this training, but it is worth noting that eASIC is a structured ASIC and offers half the power of an FPGA, but gives developers more flexibility than an ASIC. Going from an FPGA to an eASIC can help reduce design risk and is pin to pin compatible with an FPGA. This allows for a simple drop in replacement. So, with this, companies can more easily migrate their designs from an FPGA to an eASIC and then to an ASIC. And Intel really is the only company that can offer a pathway between all three: FPGAs, eASIC, and then custom ASICs. So, we've been talking about the hardware, but arguably more important than the hardware is the software that enables our hardware. Compared to other hardware companies, Intel PSG invests a huge amount of resources into our software tools and our software department. Quartus is paramount to the success of our FPGAs. You can't develop with an FPGA without the software and tools behind it. If a company wanted to enter the FPGA market, they must first have good tools. Developing a tool like Quartus, complete with a chip planner, simulator, power and timing analyzers, and debugging toolkits, all of this requires a huge upfront cost and a huge amount of resources. Not many companies can afford to do this. And the ones that can afford to do this aren't motivated to do this because we already charge very little for our software, and we even offer a free version. Because software is such a high barrier to entry, the FPGA market is likely to stay a duopoly between Intel and Xilinx. Intel and Xilinx competing head to head on the component level. But that doesn't mean our only competition is Xilinx. Now, as we move forward, our greatest competition is arguably other hardware solutions like a GPU or a custom ASIC. But this is how the FPGA ties back to broader Intel. With Intel, FPGAs are more than a component. FPGAs are part of an entire Intel solution. It's not just about whose FPGA is better, now it's about the whole package. Who can provide an entire infrastructure to make our customers successful? FPGAs complement Intel's vast product portfolio, and together we can provide our customers with one complete solution. In data centers or enterprise, you can pair a Xeon with our programmable acceleration cards. For industrial applications, you can utilize an Atom, a Cyclone, and an IoT gateway. For AI and vision, Intel has Movidius VPUs and Aria FPGAs. And in applications like 5G, Intel can be part of an entire product lifecycle from FPGA to eASIC and then to ASIC. So, this is why someone would choose an Intel FPGA, because we offer more than an FPGA. We offer one complete Intel solution. And with that, we conclude our look at the business fundamentals of the FPGA industry. To summarize, we compared FPGAs with ASICs and ASSPs. We discussed FPGA's broad customer base, the four key benefits of using an FPGA, the importance of Quartus and other software tools, and the future with Intel. For more information related to this topic, you can download PSG's free ebook, FPGAs for Dummies. For a full description of Intel FPGA products, visit intel.com, and as a follow-on course, watch our online training titled Become an FPGA Designer in 4 Hours. Intel provides multiple avenues in which to learn about the Intel FPGA products. In addition to free online training such as this, there's the Intel FPGA YouTube channel with quick videos and demos. There are virtual classes where an instructor teaches a class live over the web, and there are in-person instructor-led classes where an Intel FPGA expert teaches a topic at an office local to you. Please see the links on this slide for more detail. When using Intel FPGAs, there are many support resources that you can use as listed on this page. Be sure to check them out for any questions you might have. One last thing. When you registered for this training, a link was sent to you in your confirmation email that links to a short online survey. Please complete this to let us know what you think of this training and if you think of ways that it can be improved. Thank you for listening to FPGA Business Fundamentals. We appreciate your time, and again, my name is Justine.